really need to develop a sign in. I just, should I maybe stick my face down here in the corner and say, hello, wonderful person? Or maybe, up front say, hey, brother. Or, I don't know. I'm still working on it. Anyway, in this video, we need to look at second order homogeneous equations with constant coefficients where the roots to the characteristic polynomial are complex numbers, and do a couple of examples. So here we go. Just a reminder, we're looking at these types of equations. This is our second order homogeneous with constant coefficients. We're assuming that we can find answers of the form y equals e to the RT. Plugging that in, we get this equation that needs to be solved, and if we can find values of r that make this equation true, then we find solutions that make that equation true. So, quadratic equation, we use the quadratic formula to figure out what r is, and we are in the situation where b squared minus 4ac is negative, and so these are complex solutions that look like alpha plus or minus beta I. And in the last video, we showed how to turn that into two solutions that look like e to the alpha x times cosine beta x and e to the alpha x times sine beta x as our two solutions. Now, it occurs to me we never did show that these are independent solutions, but we could take a Wronskian and show that it's not equal to 0. That's all you'd have to do. But anyway, the general solution then looks like this, with the linear combination of those two, where I've just factored out the exponential from both terms. So let's look at our first example. Y double prime equals minus y. Now, in a regular face-to-face class, I would pause at this point and just let my students think about it for a minute, because this is a simple enough equation where they might just be able to come up with an answer, and quite often they can. Right? Do you know a function whose second derivative is equal to minus the function you started with? It's like, yeah, actually you do, and we've been working with them recently, right? Sine x and cosine x. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. So from sine x, two derivatives down, you get back to minus sine x. And so you'd have a solution to that differential equation. Likewise, if you started with cosine x, the derivative of cosine x is minus sine x. The derivative of minus sine x is minus cosine x. And so two derivatives, you'd end up with minus what you started with, and you have another solution. So without having to do much work at all here, I can see two solutions, sine x and cosine x. So the general solution would be c1 sine x plus c2 cosine x. But let's take a look at how that fits into what we've been doing, with all these complex numbers. Right? So if I were to slide the y over to the other side to make it look like we've been doing, then the a is 1, the b is 0, and the c is 1. And my characteristic equation looks like this, r squared plus 1 equals 0. This has two solutions, r equals plus or minus I, right? The square root of minus 1 or plus or minus the square root of minus 1. So what happens here is the real part of this is 0, so the alpha is 0, and the imaginary part is 1, so beta is 1 here. And the exponential piece here, the e to the 0x, just becomes e to the 0, which is 1. So it looks like it goes away. I mean, it's there, it's just 1. And then you have cosine, c1 cosine of 1x and c2 sine of 1x, which is exactly what we expected. It's always nice when you get what you expect, because you've done it two different ways and you get the same answer. That's generally a sign of good mathematics. Now let's do a look at another example that's a little more complicated. Y double prime minus 4y prime plus 5y equals 0. Again, you're assuming y equals e to the rt or e to the rx. I guess I'm using x today here for my variable. Y equals e to the rx. Did I use an x up way up there? Interestingly, I used a t. You probably picked up on this. And yeah, I'm then switching to x's. So I've said many times before in this class, t equals x. They're interchangeable. Here we go. So, characteristic equation. Solve. So, the negative b plus or minus squared b squared minus 4ac all over 2a looks like this. Which then becomes that. You got a square root of minus 4, which is 2i. So you got 4 plus or minus 2i over 2, and the 2 divides into everything here, giving you 2 plus or minus i. So the alpha here is 2, and the beta is 1. Looking like e to the 2x times the cosine, the quantity c1 cos x plus c2 sine x. There's my general solution. Now, just for the sake of example here, what if we also had an initial condition? So what if we also knew that we wanted at x equals 0, we want the y value to be 3, and at x equals 0, we want the slope to be 4. Okay. Well, plugging in that first initial condition is straightforward enough. You plug right into here for x, you plug in 0, and you say I want to get 3 out. Nicely, the sine of 0 is 0, so the c2 goes away, and we just get that c1 equals 3. Now, in order to use the second initial condition, we actually have to take a derivative first. So yeah, I'm looking at that. There's a product rule that has to happen. So there's the derivative of the exponential, and I left the sines and cosines alone. And then there's the exponential with the derivatives of the sines and cosines. Now plugging in that initial condition with y prime of 0 equals 4, saying I want a 4 out when I plug a 0 in for all these x's. There's a bunch of them there. The sine of 0 is 0, the cosine of 0 is 1, and we end up with 4 equals 6 plus c2, meaning that c2 is negative 2. And my solution, my particular solution, is this. Y equals e to the 2x times the quantity 3 cosine x minus 2 sine x. Now, when I look at the graph of that thing, there's a couple things I want to point out here. One thing is I noticed that it does get this initial condition right. Y of 0 is definitely 3. I can't see exactly what the slope is there, but it's a pretty steep slope, so I'll say 4. Yeah, that's probably pretty good. But you're not really seeing the shape of this graph. You're seeing a part of it. So I want to show you a couple different ones to get an idea of what these functions are. These solutions all have a very similar look. So rather than that graph, I'm going to look at this one. And all I've done is I've changed the e to the 2x into an e to the 0.2x. So it's still a rising exponential, but it's a much more slowly rising exponential. I kept the same sines and cosines, so 3 cosine minus 2 sine x. And what we see here is we have this vibration which is clamped in between a couple of exponentials. So in a couple of sections we'll look at more clearly what the bounding exponentials are, but this is, I believe, the square root of 13 times e to the 0.2x, and this is minus the square root of 13 times e to the 0.2x. But the idea is that you have a sine or a cosine, some sort of vibration up and down, that's amplitude is being modulated by an exponential function. This is sometimes called damped harmonic motion. Now this doesn't look damped, it looks like it's growing, right? But if the exponential were negative, in fact, let me get the next example here. So this one is same sines and cosines, but I have an e to the minus 0.2x. Right? So this is a decaying exponential. And so this vibration is getting smaller and smaller amplitude each time. The problem with the example we had with the e to the 2x is that the exponential grows so quickly and then goes down to 0 so fast that you don't notice that there's still vibrations going one way, and they were getting so big that WAMAP wasn't even drawing them. It was just graphing points that are off the top, and it didn't realize that it actually was going back up and down. Okay. But this does go up and down and hitting some exponential above and below. Yeah, damped harmonic motion. This is what we would see when anytime you have some vibration, but that vibration is getting less and less and less and less. In fact, next week, I think, we will do quite a bit with damped harmonic motion in both mechanical and electrical situations. So anyway, there is a couple of examples of second-order homogeneous equations with constant coefficients when the roots of the roots of this equation, what is it called? The characteristic equation, are complex numbers. Have fun.